Section 1.5, divisibility. We start with the following definition. If A and B are integers, and if A is not equal to 0, we say that A divides B if there is an integer C such that B is equal to AC. If A divides B, we also say that A is a divisor or a factor of B. Notation. Vertical line means D divides N, or which is same, N is divisible by D. For example, 4 divides 12 because 12 is equal to 4 times an integer, which is 3. 4 does not divide 15 because 15 is 4 times a non-integer number. Theorem 1. Let A, B, and C be integers, and A, B are not equal to 0. If A divides B and B divides C, then A divides C. It's exactly what is written here. How we prove it? A divides B. Once again, it's given. A divides B. A divides B means B is A times an integer. Similarly, B divides C means C is B times an integer. And now let us start from this. It's over here. And replace B by AE. If we replace B by AE, we get this. Lastly, let us shift parentheses to the right. AE times F is equal to A times EF. Since both E and F are integers, EF is an integer number. So C is equal to A times integer, which by definition of divisibility means A divides C. Example, 7 divides 56, 56 divides 168, therefore 7 divides 168. Theorem 2. Let A, B, C, M, and N be integers. And suppose C is not equal to 0. If C divides both A and B, then C divides any their integer linear combination. By linear combination of A and B, we mean this expression: A times M plus B times M. We call this a linear combination of A and B. So, no matter what is M and N, if M and N are integers, C divides this. In particular, if M is equal to 1 and N is equal to 1, C divides A plus B. So, if C divides A and C divides B, C divides their sum. Or, if we put M is equal to 1 and N is equal to -1, this becomes A minus B, Conclusion: if C divides A and C divides B, C divides A minus B. So these are two particular cases of this general theorem. How do we prove it? Once again, we start from this and this. C divides A means A is equal to C times K1. C divides B means B is equal to C times K2, where K1 and K2 are some integer numbers. Now, we start from MA plus MB. We replace A by this, done. We replace B by this, done. Lastly, factor out C, done. Note that since M, N, K1 and K2 are integer numbers, this is an integer. Conclusion: MA plus MB is C times an integer. Therefore, by definition of divisibility, C divides MA plus MB. In particular, 11 divides 22, 11 divides 33, therefore 11 divides 319 because 319 is an integer, a linear combination of 22 and 33. Folks, any questions here?
I have a question.
Yeah.
In the homework and on the test, so like you're explaining like through your proof, telling us, well, we see that MK, N, and K2 are all integers, so we know that that's an integer, but it's not written in your proof. So on the homework and on the test, do you expect us to write those out, or is like if we write it like how you write it, that's going to be fine?
Excellent question. If you do this, it's absolutely enough.
Okay, thank you.
So once again, during a lecture, I provide even more details than it's written here. But on tests, you do not have to be as detailed as I am right now. Next, here's an example. Show that 8 divides n squared minus 1 if n is 4k plus 1, where k is an integer. How do we do that? We start with n squared minus 1. Step 1, replace n by 4k plus 1. Done. By algebra, a plus b squared is a squared plus 2ab plus b squared. Cancel out 1, done. Factor out 8. Note that since k is an integer, 2k squared plus k is an integer. So n squared minus 1 is 8 times an integer. Therefore, 8 divides n squared minus 1 by definition of divisibility. Similarly, in order to show that a minus b divides a squared minus b squared, where a and b are integers and a minus b is not equal to 0, we just observe that by algebra a squared minus b squared is a minus b times a plus b. So a squared minus b squared is a minus b times an integer. Therefore, a squared minus b squared is divisible by a minus b. I encourage you to take a look at all examples from Appendix 1. There are lots of important examples. Next, Theorem 3, division algorithm. Theorem 3 is of a great importance in number theory. We will deduce other important theorems from Theorem 3. So, Theorem 3 says the following. Suppose A and B are integer numbers where B is not equal to 0. Then, there exist unique integers Q and R such that A is equal to BQ plus R, where R is greater or equal to 0 and strictly lesser than absolute value of B. We call Q quotient, we call R a remainder. This theorem looks dry, but actually there are lots of important applications. Let me give you one really simple example. If B is equal to 2, this theorem says the following. Any integer A can be written uniquely as 2Q plus R, where R is greater or equal to 0 and strictly lesser than absolute value of 2, which is 2. But now, since R is an integer and R is greater or equal to 0 and lesser than 2, we have only two possibilities for R. R is either 0 or 1. In other words, any integer A can be written as 2Q plus either 0 or 1, which means all integers can be split into two non-overlapping groups, even numbers when R is equal to 0 and odd numbers when R is equal to 1. These groups are non-overlapping thanks to uniqueness. Okay, how do we prove this theorem? Here we provide two different proofs of this theorem. Proof 1. Consider the set S of all integers of the form A minus BK, where K is an integer. So once again, A is given, B is given. K can be any integer. So S is the following set of integers, A minus BK, where K is any integer number. Now, let us consider a subset of S. Let us denote this subset by T. T is a subset of all non-negative integers of these four. Let us first show that set T is non-empty. One can say, well, our intuition tells us that no matter what is A and no matter what is B, it is always possible to find an integer, actually infinitely many integers K, such that A minus BK non-negative. Well, guys, but let us prove it rigorously. So, we want to show that no matter what is A and B, there exists K such that A minus BK is greater or equal to 0. Please take a look at Appendix 3. We want to prove that it is always possible to find an integer solution of this inequality. Well, let us move BK to the right, we get this. Now, let us divide both sides here by B. We can always do it. Because, let me remind you, b is a non-zero number. But now be careful. When we divide both sides by b, if b is greater than 0, we do not change the sign. However, if b is lesser than 0, when we divide both sides by b, we switch the sign. Now, after the cancellation, this becomes the following. K is lesser or equal to a over b. It's exactly what is written here. After the cancellation here, we get the following. K is greater or equal to a over b. It's exactly what is written here. So, it's absolutely obvious that no matter what is a and what is b, it is always possible to find an integer which is lesser or equal to a over b. Similarly, no matter what is a and b, of course, as long as b is not equal to 0, it is always possible to find an integer k which is greater or equal to a over b. But since this implies this and this implies this, it is always possible to find an integer number k such that this is greater or equal to 0, therefore set t is non-empty. Any questions here?
So everything we just did so far was just to prove that t is non-empty?
Yes, absolutely. And we proved that t is non-empty using the following approach. We just showed that no matter what is a and what is b, it is always possible to find an integer k such that this is indeed non-negative.
Okay.
So once again, here I give you two approaches. Our intuition tells us that t is non-empty because our intuition tells us that no matter what is a and b, if b is non-zero, it is possible to find k such that this is greater or equal to 0. But over here, I provide a rigorous proof.
If we were to write this proof out again, would we be expected to write out the proof, the small step in Appendix 3, or is that already known that it's non-empty?
So your question is, what if I include theorem into a test? Do you have to provide these explanations? The answer is no.
Okay, thank you.
All right. Since t is the set of all non-negative integers, and since t is non-empty, we can apply the well-ordering property. By the well-ordering property, t has a least element. Let us denote this least element by r. The goal is to show that our r satisfies the following double inequality. R is greater or equal to 0, and r is lesser than absolute value of b. Now, this portion is absolutely obvious because r is an element of t, and t consists of only non-negative integers. So r is non-negative. R is greater or equal to 0. Hard part is to show that r satisfies this. Let us prove that r is lesser than absolute value of b. We will prove it by contradiction. Assume to the contrary that r is greater or equal to absolute value of b. Step 1, move this to the left. Done. Here is what we do next. Copy this over here and replace R, which is this, by A minus BQ. Done. We replace R by A minus BQ. Next step. Please take a look at this portion. Over here, let us factor out D. If we factor out D in parentheses, we get the following: Q plus absolute value of B over B. Well, here's why. Let us expand parentheses back. If we expand parentheses here, we'll get the following: negative B times Q, which is this, minus times plus minus, and then B times absolute value of B over B. After the cancellation of B, we will get absolute value of B. So indeed, this is equal to this. Next observation. Let us denote this expression Q plus absolute value of B over B by K. Now, let us show that K is an integer. Well, here's why K is an integer. K is equal to this. Q is an integer. Absolute value of B over B is an integer again, because absolute value of B over B can be either 1 or -1. Indeed, if B is positive, suppose B is 5. Absolute value of 5 divided by 5 is 1. Now, suppose B is negative, say -7. Absolute value of -7 is +7, divided by -7 is -1. So, this is an integer, this is an integer, plus minus 1. Therefore, the whole thing is an integer. So, K is an integer number. Conclusion. This is of the form A minus B times integer. Therefore, R minus absolute value of B is an element from S. Moreover, R minus absolute value of B is an element from T, because R minus absolute value of B is from S and is greater or equal to 0. Once again, conclusion, R minus absolute value of B is from T. We get a contradiction. Here is why. Since B is not equal to 0, absolute value of B is strictly greater than 0. Therefore, R minus absolute value of B is strictly lesser than R. Cannot be. We just said that R is the smallest element from T. But it turns out that R minus absolute value of B is again from T and smaller than R. Since we get a contradiction, this is impossible. Therefore, R is strictly lesser than absolute value of B. All right. Here is what is left to prove. We should prove uniqueness. So part 2. Let us show that values of Q and R are unique. In order to do that, assume that we have two equations. A is equal to BQ1 plus R1, and A is equal to BQ2 plus R2. The goal is to show that Q1 is equal to Q2 and R1 is equal to R2. Let us subtract this from this. A minus A is 0. BQ1 minus BQ2 after we factor out B is this. And lastly, over here we have R1 minus R2. Next step. Let us move this to the left. We get the following. R2 minus R1 is B times Q1 minus Q2. Next step. Note that since R1 satisfies this inequality and R2 satisfies this inequality, R2 minus R1, which is over here, satisfies this double inequality. Question is, how come that this follows from this and this? Note that if we have two inequalities, we can add these inequalities, but we cannot easily subtract inequalities. We cannot just subtract R1 from R2. Note that if we just subtract this from this without changing anything, we'll get 0 minus 0, 0, absolute value of B minus absolute value of B is 0, and we'll get an absurd R2 minus R1 is greater or equal to 0 and lesser than 0. So how do we subtract this from this correctly? Let us go to Appendix 3 again. Remark 2. So once again, we have this and we have this. Let us show that this double inequality and this double inequality imply this double inequality. To this end, let us multiply double inequality number 1 by negative 1. Since we multiply by a negative number, we have to switch the signs. So, if we multiply both sides here by negative 1, we get the following. 0 times negative 1, R1 times negative 1, and we switch the sign. Similarly here, if we multiply both sides here by negative 1, we switch this sign again. And now, negative 1 times absolute value of B is negative absolute value of B. 0 times negative 1 is 0. Negative 1 times R1 is negative R1. We put this on the left and this on the right. So we just rewrite this in this way. And now let us add two inequalities. Let us add this and this. 0 plus negative absolute value of B is negative absolute value of B. R2 plus negative R1 is R2 minus R1. Absolute value of B plus 0 is absolute value of B. So now we see that indeed this and this imply this. Lastly, let us show that this in combination with this imply the following. Q1 minus Q2 is equal to 0. First of all, again, it's kind of common sense. Think about this. R2 minus R1 is strictly between negative absolute value of b and absolute value of b. But R2 minus R1 is b, same b is here, times an integer. If you think a little bit, this actually almost immediately implies that there is no escape. This has to be 0. But let us do it rigorously. Remark 3. So once again, here's what we have. We have this. It's this double inequality. And we have this. It's 1. So let us prove that this and this imply this. Here's how we do it. First of all, let us replace this expression over here by this. If we replace this by this, we get this. Next step. Let us divide all 3 parts of this double inequality by absolute value of b. Since absolute value is strictly greater than 0, we do not switch the signs. Negative absolute value of b divided by absolute value of b is -1. Absolute value of b divided by absolute value of b is 1. And lastly, here we get the following. B divided by absolute value of b times q1 minus q2. As we discussed, b over absolute value of b is an integer which is equal to either 1 or -1. Conclusion: since this is an integer and this is an integer, the whole thing is an integer. But now, an integer number is strictly greater than -1 and strictly lesser than 1. How can this be? The only integer which is strictly greater than -1 and strictly lesser than 1 is 0. Conclusion: this, which is over here, is equal to 0. But remember, b is not equal to 0. Since b is not equal to 0, this is not equal to 0. But the product is 0. Conclusion: there is no escape. q1 minus q2 is equal to 0. It's exactly what we have here. Finally, since q1 minus q2 is equal to 0, q1 is equal to q2. Very last step. Remember, this and this are equal to a. Therefore, bq1 plus r1 is equal to bq2 plus r2. This is what we have over here. q1 is equal to q2. Therefore, bq1 is equal to bq2. We cancel out this term and we get the following. r1 is equal to r2. So q1 is equal to q2. R1 is equal to R2, which proves uniqueness. Next, proof 2. In proof 2, we distinguish 2 cases. Case 1, b is greater than 0. Case 2, b is lesser than 0. Suppose b is greater than 0. In proof 2, we have explicit formulas for both q and r. By the way, this formula immediately follows from this and from this. Indeed, according to what is written here, r is a minus bq. Therefore, If Q is floor of A divided by B, R is A minus B Q. What is floor? Floor is the greatest integer which does not exceed this. So these are explicit formulas for Q and R. The question is it true that these are indeed satisfies this double inequality? First, let us show that R is greater or equal to 0. So once again, by what is written here, R is A minus B times floor of A divided by B. Observe that since floor is the biggest integer that does not exceed this, the left-hand side is lesser or equal to A divided by B. Since this is lesser or equal to A divided by B, and since here we subtract, this term is greater or equal to negative B times A over B. Lastly, cancel out B, we get A, and A minus A is 0. Conclusion, R is greater or equal to 0. Now let us show that R is lesser, strictly lesser than absolute value of B. Since floor of A divided by B is the biggest integer that does not exceed this, floor of A divided by B is strictly greater than A divided by B minus 1. Now, R is this, which is over here. Since this is greater than A over B minus 1, what is written here is lesser than this. And now expand parentheses, minus times minus plus, cancel out B. A minus A is 0. What is left is B. And since B is greater than 0, B is equal to absolute value of B. So R is lesser than absolute value of B. Since R is greater or equal to 0 and lesser than absolute value of B, R indeed satisfies this double inequality. Case B. Suppose B is lesser than 0. Then formulas for Q and R are different. Instead of the floor function, we use the ceiling function. Ceiling of A divided by B is the smallest integer, which is greater or equal to A divided by B. Again, as before, let us show that R, which is equal to this, satisfies this double inequality. By the nature of the ceiling function, ceiling of A divided by B is greater or equal to A divided by B, because this is the smallest integer, which is greater or equal to A divided by B. So, ceiling of A divided by B is greater or equal to A divided by B. B is lesser than 0. Therefore, we have the following. R is equal to this. It's over here. According to what is written here, negative B times ceiling of A divided by B is greater or equal to negative B times A over B. Cancel out B. A minus A is 0, so R is greater or equal to 0. In order to show that R is lesser than absolute value of b, observe that ceiling of a divided by b, guys, here is a misprint. Instead of b should be a divided by b. So ceiling of a divided by b is strictly lesser than a divided by b plus 1. So we replace this by a divided by b plus 1, expand parentheses, cancel out b, done, cancel out a, the result is negative b, but remember b is strictly lesser than 0. Therefore, negative b is equal to absolute value of b. So r is greater or equal to 0, r is lesser than absolute value of b, therefore r satisfies this double inequality. Lastly, we prove uniqueness in the same way as in proof 1. Now examples. Let a is 49, b is 4. Observe that 49 is equal to 4 times 12 plus 1. Therefore, quotient is 12, a remainder is 1. Now let us play with pluses and minuses. Suppose a is 49, b is negative 4. Then quotient is negative 12, a remainder is 1. To the contrast, if a is negative 49, b is positive 4, quotient is negative 13, a remainder is 3. Similarly, if a is negative 49, b is negative 4, quotient is positive 13, remainder is 3. Here's what I'm trying to say. If you switch a sign here and or switch a sign here, it does not necessarily mean that as a result we switch a sign here and or we switch a sign here. Compare this and say this. We replace 49 by negative 49. As the result, the remainder is totally different. Instead of 1, we have 3. Also keep in mind that remainder is never negative. Quotient can be negative. A remainder is always greater or equal to 0. Here's another way to come up with these numbers. Let us use the formulas from proof 2. We start with a is 49, b 4. Note that since b is positive, we apply these formulas. So, floor of 49 divided by 4. 49 divided by 4 is 12.25. The biggest integer that does not exceed 12.25 is 12. It's exactly what we got here. Now, in order to find r, we use this formula. A is 49, b is 4, floor of 49 over 4 is 12. We put here 12. 49 minus 48 is 1. So these formulas allow us to find quotient and a remainder without guessing. Similarly, over here, b is positive again. Therefore, again, we use these formulas. So, floor of negative 12.25. Note that now this number has nothing to do with negative 12. Remember, floor means biggest integer that does not exceed this. We go, in other words, always to the left. The biggest integer that does not exceed this is not negative 12, it's negative 13. And now we plug in negative 13 here. Negative 4 times negative 13 is positive 52. Negative 49 plus 52 is 3. So now quotient is negative 13, remainder is 3. Now consider two other examples. In both cases, b is negative. Therefore, instead of the floor function, we use the ceiling function. Ceiling of negative 12.25 is negative 12. This is the smallest number, which is greater or equal to this. We have to be from the right. We plug in negative 12 here, a remainder is 1. To the contrast, ceiling of 12.25 is 13, smallest number, which is greater or equal to this. We plug in 13 here, a remainder is 3. Next, let us go back to theorem 3. Suppose b is equal to 2. As we discussed, if b is equal to 2, there are only two possibilities for the remainder. R is either 0 or 1. Please take a look at this definition. If the remainder when n is divided by 2 is 0, then n is 2q, and we say that n is even. Now, if the remainder is 1, then n is 2q plus 1, and we call n odd. Thanks to the division algorithm, for any integer n, there are only two possibilities. N is of the form 2q, or n is of the form 2q plus 1. Therefore, any integer is either odd or even thanks to existence, but not both, thanks to uniqueness. Similarly, if b is equal to 3 in the division algorithm, we come up with the following conclusion. Any integer n is either of the form 3q, or 3q plus 1, or 3q plus 2. Let me show you how we use this to come up with a very non-trivial result. Please take a look at this example. In this example, we show the following. Suppose k is an integer. No matter which integer we plug in here, k squared minus 2 is not divisible by 3. Here's how we prove it. Note that according to what is written here, for k, we have only 3 possibilities. K is either of the form 3q, or of the form 3q plus 1, or of the form 3q plus 2. Now, assume to the contrary that for some k, k squared minus 2, which is over here, is divisible by 3. Well, now let us replace k first by this, then by this, and then by this. If over here we replace k by 3q, this term becomes 9q squared. Note that negative 2 can be rewritten as negative 3 plus 1. Lastly, factor out 3 here. Done. And denote this by s. Conclusion. If k is equal to 3q, k squared minus 2 is of the form 3 times integer plus 1. But note that if k squared minus 2 is divisible by 3, k squared minus 2 is of the form 3m plus 0. According to what is written here, if k is equal to 3q, the remainder is 1. Therefore, the remainder cannot be 0. We got a contradiction. Similarly, if over here we replace k by 3q plus 1, we jump from here to here, we expand parentheses, plus 1 minus 2 is negative 1, negative 1 is negative 3 plus 2, factor out 3, denote this by s. Conclusion: if k is of the form 3q plus 1, this is of the form 3s plus 2, so the remainder is 2, which is again not equal to 0. Conclusion: if k is 3q plus 1, this is impossible again. Lastly, if k is 3q plus 2, we replace k by 3q plus 2, we do algebra. Conclusion: the remainder is 2, so 0 is impossible again. Once again, we come up with the following result. No matter what is k, 3q, or 3q plus 1, or 3q plus 2, this cannot be of the form 3 times integer plus 0. Folks, any questions here?
Could you reiterate how you came up with the 3 possibilities? How you knew what the 3 possibilities were, the 3q and the 3q plus 1, 3q plus 2?
Your question is how we come up with this?
Yes.
It's by this. If in the division algorithm, if in theorem 3, we set b is equal to 3, r is greater or equal to 0 and strictly lesser than 3. So for r, we have only 3 possibilities. R is either 0, or 1, or 2. It's exactly how we come up with this result. If r is equal to 0, n is 3q. If r is equal to 1, n is 3q plus 1. If r is equal to 2, n is 3q plus 2. And by the division algorithm, there are no other possibilities. Was that your question?
Yeah. I'm not sure how we go from that to where we assume to the contrary that there's an integer number k, such that k squared minus 2 is divisible by 3. I'm not sure how we made the jump.
No. We want to prove that 3 does not divide k squared minus 2.
Right.
Assume to the contrary that k squared minus 2 is divisible by 3 for some integer k. If k squared minus 2 is divisible by 3, k squared minus 2 is 3 times some integer, correct?
Yeah.
But now, thanks to this, for this k, there are only 3 possibilities. K is either 3q, or 3q plus 1, or 3q plus 2. But if k is 3q, according to what is written here, the left-hand side, which is over here, is of the form 3s plus 1. Note that according to the division algorithm, when we divide same number by 3, the remainder is unique. Therefore, there is no way we can get two different remainders, 0, and here the remainder is 0, and 1. Here the remainder is 1. Does this make sense?
Yeah, that makes sense now. Thank you.
And now, same here. If k is of the form 3q plus 1, the remainder is 2. Therefore, it's not 0. Lastly, over here, the remainder is again 2, which is not 0. Last part, greatest common divisors. A common divisor of two integers a and b, which are not both 0, is an integer c that divides a and b. Greatest common divisor, in short, GCD, which we denote by a comma b in parentheses, is the largest common divisor of integers a and b. For example, let us consider the following two integers. A is 24, b is 84. Common divisors are plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, and plus minus 12. Looking at what is written here, the greatest common divisor, which we denote by 24, 84 in parentheses, is 12. Similarly, greatest common divisor of 15 and 81 is 3, 105 is 5, and so on, guys. Lastly, we say that two integers are relatively prime if their greatest common divisor is equal to 1. Relatively prime does not mean prime. Note that 12 is not a prime number. 25 is not a prime number. But since their greatest common divisor is 1, we say that 12 and 25 are relatively prime.